In today's module, we're going to discuss degenerate perturbation theory. First, a quick reminder of the results of normal or just regular perturbation theory, which we use when we know how to solve a Schrödinger equation for some zeroth order Hamiltonian to obtain the zeroth order wave functions and their energies. Here the subscript stands for zeroth order, and the superscript stands for zeroth order, and the subscript labels the energy level, the wave function and its energy level. And we want to solve a general Schrödinger equation and so we write our general Hamiltonian as the zeroth order Hamiltonian we know how to solve, plus a first order term and possibly higher order terms. And likewise, we write the energy level as the zeroth order energy plus a first order term and possibly higher order terms and the wave function. And then we can derive a first order correction to the energy of energy level n, which is the expectation value of the first order correction to the Hamiltonian for the zeroth order wave functions for energy level n. And we can also derive the first order correction to the wave function, which is a linear combination of the zeroth order wave functions with coefficients given by this integral divided by the energy difference between energy levels n and k. And we can see immediately that there's a problem in the case that the zeroth order wave function has degenerate eigenfunctions. And what we mean by that is that H0 on psi 1 of 0, say, is equal to E0 psi 1 of 0, and HC0 acting on psi 2 of 0, say, is equal to the same energy E0 times psi 2 of 0. For the case when psi 1 of 0 and psi 2 of 0 can be chosen to be orthogonal. And we can see very straightforwardly then the equation for the first order correction to the wave function simply can't be used because it has a 0 in the denominator. At first glance, it looks like one could still calculate the first order correction to the energy, but that turns out also not to be true, because we know that when psi 1 of 0 and psi 2 of 0 are degenerate, they have the same energy, they're both eigenfunctions of the same operator with the same eigenvalue, then any linear combination of them, let's just write it as psi of 0, which is alpha psi 1 of 0 plus beta psi 2 of 0, is also an eigenfunction of H0. And so we can't even calculate the first order correction to the energy because we don't know what to use for our unperturbed wave function. So it's clear that we're in trouble and we need another approach. And the approach that we use is called Degenerate Perturbation Theory. So let me first write down what we do, the method that we use, and then we'll look at an example, and then at the very end, we'll go through the mathematical proof of this method. Okay, so the method for finding the correction to the energies and the eigenfunctions is as follows. And I'm going to write down the method when we have two degenerate states, and then we'll extend it to a higher number later. So we're going to write down the matrix, which is often called W, and it looks like this. Its elements are the integral of psi 1 of 0, the first zeroth order wave function, with the first order correction to the energy, psi 1 of 0, psi 1 of 0, H1, psi 2 of 0, and then psi 2 of 0, H1, psi 1 of 0, psi 2 of 0, H1, psi 2 of 0. So we write down this matrix by calculating all of these integrals. and find its eigenvalues and eigenvectors. And the eigenvalues are then the first order corrections to the energies, and the eigenvectors are the first order corrections to the wave functions. Often one works with this matrix. It's also possible and sometimes convenient to use H0 plus H1 here, and then one obtains directly the energy, which is the sum of E0 of the 0th order energy plus the first order correction. And of course, the way that we find the eigenvectors and eigenvalues is to multiply this matrix by the coefficients alpha and beta, which are the coefficients in the eigenvector, and this is equal to then first order energies times the vector of the coefficients. Let's write down trivially the case for the eigenvalues. By solving the determinant of the W matrix minus the first order corrections to the energy, which is solving for times the identity and setting it equal to 0. Then we see straightforwardly that we have W11 minus E1, W12, W21, W22 minus E1 is equal to 0, or the two values of the first order correction to the energy are a half W11 plus W22 plus or minus the square root of W11 minus W22 squared plus 4 times W12 squared, and solving for alpha and beta would give us the wave functions. So this is the approach if we have 3 degenerate states. This will give us a 3 by 3 matrix. 4 degenerate states, a 4 by 4 matrix, and so on. So let's apply this using an example, and then at the end we'll formally derive where these equations came from. So I want to look at the example. It's going to be an example of a 4 by 4 case of an electron in an n is equal to 2 atomic orbital of the hydrogen atom with an electric field strength E applied along the z-axis. Let's, before we do any mathematics, just think about what this would look like. I realize I have the wrong shape bracket over here. I'm going to fix it so it looks ugly. So when E is equal to 0, then we know that the energy of the n is equal to 2 atomic orbitals all have the same energy. They're all degenerate, and there are 4 of them, which are the 2s, the 2px, the 2py, and the 2pz. And when the electric field is equal to 0, it's equal energy for the electron to be in any of those 4 orbitals. Now, just by inspection, if we think of the symmetry of the 2px and the 2py orbital that are lying in the xy plane, when we apply an electric field along z, their energies are going to be unchanged. And so now when we have an electric field parallel to z, as we increase the size of the electric field, the px and the py orbitals are not affected by the electric field. Their energies are unchanged. So along this axis here, I'm increasing the size of the electric field. The other 2 orbitals in a linear combination will have their energies changed, and we'll see that which linear combination they form will drop out of the mathematics. But if we just think about it first, the linear combination consisting of S minus PZ looks like this. If we assume that our s orbital has positive phase, then its shape as a dipole has a lot of electron density at the bottom and only a little electron density at the top. So it has a dipole which is parallel to the electric field direction. And so its energy, it's lowered as the electric field is applied, whereas the orbital, which consists of the s orbital plus the pz orbital, again, if we assume that the s orbital has positive phase, and we add that to a p orbital oriented with its positive phase along plus z, then it has a dipole that's anti-parallel to the electric field, and so its energy increases as the electric field is increased. So just intuitively, we see that 2 of the atomic orbitals are unaffected by the electric field. The linear combinations of the 2 remaining ones, one of them is lowered by the electric field and one of them is increased by the electric field. So the degeneracy is lifted by the electric field. Let's write that down mathematically. our W matrix looks like this. So the basis for our matrix are our four orbitals that we start off with, S, Px, Py, and Pz. And our terms are the wave function of the 2s orbital times our perturbation to the Hamiltonian, which is our electric field, times the wave function. Oh, sorry, let me correct myself here. Let me clarify that I'm going to write the W matrix in terms of just the perturbation of H1. I'm not going to include the H0 term. And so then my first term in the top left then is the wave function of the s orbital times the electric field along the z direction times the wave function of the s orbital, which I can immediately, by symmetry, write down is 0 because both s orbitals are even and the electric field along the z direction is odd. The same thing for the term with px. And py and pz. So I have zeros on the diagonal of my matrix. For the off-diagonal terms, then these look like this: psi s times e along the z direction times psi px. And this one is also 0 by symmetry. Likewise for py. But for pz, since the electric field is along the z direction and pz is along the z direction, I don't get a 0 here. So this term survives, whereas all other terms except psi pz times the electric field along z times psi s are 0. So I can see that my matrix is actually block diagonal. I can reduce this to two 2 by 2 matrices. One in a basis of px and py, which is just all zeros, which shows us immediately that there's no change in the energies of the px and y orbitals. And the other, which is in the basis of s and pz, has these non-zero terms. Let's call them w s pz. And I can solve this equation and find that my first order corrections to the energy then R plus and minus this W SPZ quantity. If I then substitute back and solve for the eigenvectors, I'll find that the eigenvectors are 1 over root 2, the wave function of the s orbital, plus or minus the wave functions of the 2pz orbital. The 1 over root 2 is for normalization, of course. So this is exactly what we obtained just by intuition. If we'd been really smart and from the start recognized the way that our wave functions would be affected by the electric field, we could have in fact written our W matrix in terms of a basis of Px, Py, S plus Pz, and S minus Pz, and we would have found it was diagonal to start with. We would have actually had nothing to solve. It would have directly given us the answer in that case. Okay. So that's an example of how this works. Now let's finish up by doing the derivation. So we want to solve the Schrödinger equation. With h given by h0 plus lambda h1 and energy given by E0 plus lambda E1 plus lambda squared. So E2 and so on, and our wave function given by psi 0 plus lambda psi 1 plus lambda squared psi 2 and so on. And our psi 0 in this case is alpha psi 1 of 0 plus beta psi 2 of 0. So we're not solving in this case separately for psi sub n with n is equal to 1, psi sub n with n is equal to 2, or because our wave functions are degenerate, so we're taking a general linear combination of them. Okay, so then substituting these into the Schrödinger equation, and collecting like powers of lambda, and then keeping only the terms in order lambda 1, we obtain an equation h0 psi 1 plus h1 psi 0 is equal to E0 psi 1 plus E1 psi 0. And this procedure is exactly the way we proceed in conventional perturbation theory. Now we'll use the trick of pre-multiplying by psi1 of 0 and integrating over all space, which is what we call taking the inner product. And that gives us this equation here, psi1 of 0, h0, psi1, plus psi1 of 0, h1, psi 0 is equal to E0, psi1 0, psi1 plus E1, psi1 0, psi 0. So let's see how we can simplify this. So first, in this term, H0 acting on psi1 of 0, we know is just E0, psi1 of 0. So we can simplify this term to E0, psi1 0, psi1. Remember, because H is Hermitian, H0 is Hermitian, we can operate either to the left or to the right, it's equivalent. And so then we can cancel this term on the left with the equivalent term on the right, which is this one. Then the next simplification that we can make is to remember that psi 0 is alpha psi 1 0 plus beta psi 2 0. And of course, since psi 1 of 0 and psi 2 of 0 are orthogonal, psi 1 0, psi 2 0 gives us 0 here. So this term here, the integral reduces to alpha, and the whole term simplifies to E1 times alpha. Then we can write out our psi of 0 as alpha psi 1 of 0 and beta psi 2 of 0, and we obtain the following. That alpha psi 1 0, h1 psi 1 0 plus beta psi 1 0, h1 psi 2 0 is equal to alpha E1. And here my psi 0 gave me an alpha psi 1 of 0 over here, and the beta psi 2 of 0 over here. Okay, we can do the same thing with taking the inner product with psi 2, or let's first write this more compactly as alpha W11 plus beta W12 is equal to alpha E1, where W11, W12 have the same meanings we introduced before. Okay, then we can take the inner product in exactly the same way with psi 2 0, and that gives us alpha W21 plus beta W22 is equal to beta E1. So here with this trick, we've ended up with two simultaneous equations. And of course, one way that we can solve these is in matrix form as W11, W12, W21, W22 times the vector of coefficients alpha beta is equal to the first order correction to the energy times alpha beta. And this is exactly the form that we wrote down to use at the start. So that's it for today, and thanks for listening.